In lecture 27, we talked about carrier diffusion and we talked about the optical transitions, specifically the different situations in direct and indirect bandgap semiconductors. So first, you should be able to describe the cause of diffusion currents and the factors that are influencing those currents. Similar to many other diffusion processes in materials, the diffusion of carriers is driven by the concentration gradient. And because electron and holes have opposite type of charges, the diffusion current for electron holes may be in the same direction as the concentration gradient or in opposite direction of the concentration gradient. And these diffusion currents will be added on top of the drift current that we already discussed earlier, that give you a total current for both electron and holes. And remember, there is also Einstein relationship relating the diffusion coefficient or diffusivity of the electrons to the corresponding mobilities, and similarly for holes. The second student learning outcome is to describe the thermalization process and why optical transitions are called vertical transitions. So this is a scheme for excitation of electrons from the valence band to the conduction band after the electron absorbs a photon. And obviously with the this optical transition, the minimum photon energy needed is to provide the electron transition from top of the valence band to the bottom of the conduction band. That means the photon energy has to be at least the band gap, but it could be greater. And this is so-called band-to-band or interband transition. And since the average kinetic energy of electrons in conduction band is only 3½ kT, similar for average kinetic energy hole in the valence band, 3½ kT. Eventually, under thermal equilibrium, these electron holes will, instead of having a very high energy, they're actually going to thermalize and reduce those kinetic energy to 3½ kT, and this is called thermalization. So basically, when the electron is having very high kinetic energy, appears to be very hot. Temperature is high, so through collision with lattice atoms, the kinetic energy of that electron will be lost, eventually get to thermal equilibrium. And this is a very rapid process, only on the order of picosecond. Now, why do we call this a vertical transition? Because we do have energy conservation and also momentum conservation in these transitions. And the energy conservation gives you the photon energy requirement. Minimum will be the band gap, and this is an extremely fast process. But now let's look at photon momentum. Photon momentum is inversely proportional to the wavelength of photon, and for the wavelength of the photon is actually much higher than the wavelength of the electron wave. So that's why the momentum of the photon is negligible compared to the momentum of the electron. So that's why when we consider the momentum conservation, we don't need to consider the photon momentum. That's why the momentum of the electron in the valence band and momentum in the conduction band will be the same. That's why it appears in this EK diagram, in the band structure diagram, they appear as these so-called vertical transitions. The third student learning outcome is to relate the photon energy to the band gap of semiconductor during light absorption or emission processes. So in the light absorption process, this is what we had earlier. Photon is absorbed, that drives the electron from the valence band to the conduction band, and we have thermalization of those electron and hot holes to the bottom of the conduction band and top of the valence band. That's the absorption process, okay, light absorption process. Okay, photon energy minimum is the band gap, but it could be higher. And the excess energy, if it's greater than the band gap, that this excess energy will be eventually converted to heat in the lattice through the thermalization process. On the other hand, once the electron sits in the bottom of the conduction band and holes it at the top of the valence band, they may recombine. And this recombination, if it is a radiative process, it will generate a photon. So this is also called luminescence process. And because the average kinetic energy of the electron and hole is very small, 3½ kT, so the energy that will be released through this recombination is basically the band gap. So that's why for light emission, the band gap basically determines the energy of the photon emitted, and so that's why you can determine on the wavelength of the light emission from the semiconductor. The last student learning outcome is to describe why phonons are needed and how they assist optical transitions across the band gap for indirect band gap semiconductors. So when we look at the transitions in the direct band gap semiconductor, the conduction band minimum and the valence band maximum are at the same K location. So in that case, the transition of electron across the band gap does not require momentum change. So a photon can just do it. But when we have an indirect bandgap semiconductor, in which case the conduction band minimum and the valence band maximum are at different k locations, we do involve a significant change in the momentum as the electron goes across the band gap, from top of the valence band to the bottom of the conduction band in the absorption case, or from bottom of the conduction band to the top of the valence band in the luminescence process. So that means that photon is not enough. We also need to have some particle that can change the momentum of the electron that can be provided by a phonon. So in this case, phonon is required, either absorption of a phonon or generation of phonon. Then that can happen in either case. So in the case of photon absorption, when we have three particles, electron, phonon, and photon, the typical process is going to be slower. So that gives you a slower rate for light absorption. Similarly, for emission, the process the radiative process will also be slower. That means that we now have the competition of non-radiative recombination that will take all these energies away. So this is the end of the review.